dynamic hydrophobicity. So let me start the introduction. 听到声音？First is our outline. The introduction is we are looking into a phenomenon that is when a drop is dropped on the high velocity surface, it won't it won't break and stay on the surface. Instead, it will rebound and it will not wet the surface. So the theory we use is first one, Young's theory. We use this to describe the contact angle and the surface tension. Next one is our motivation. We knew this problem from the International Young Physics Tournament. And this is the competition that asks students to investigate on themselves into like specific science questions. So this is one of them from the year of 2021, dynamic hydrophobicity. Dynamic means high velocity and hydrophobicity is like determining the wettability. This topic can apply in daily scenario and it's a innovative notion. This is an example of the phenomenon can be used in our lives. This is a trend in a snowy country. So you can see there is a circle glass, and there's a motor in the middle. So when it's raining or snowing very heavily outside, this this piece of window started to rotate very fast, like about 1500 RPM. And by doing this, you can prevent the snow or any rain stay on this piece of window, so you can always have a very clear sight to the road in front of you. And I think this topic can apply in an anti-flooring field in the future that could prevent things to get dirty and always be clean. Like for example, the lotus, one kind of plant lotus has a very tiny structure that water doesn't stay on it, so it can always be very clean. The section 2 is problem. We have phenomenon and theory. The phenomenon of this research is basically talking about the contact angle. The contact angle is determined by the surface structure and surface tension. So in this case, we use the material we use is the PC, like this one, the PC surface. In this case, we will have a contact angle of 56.3 degree, that is less than 90 degrees. So we will say this surface is not hydrophobic. So water will wet this surface. But in a dynamic, which means high-speed surface, like when this surface started to move very fast, the water provides water a contact angle over 90. So it's considered hydrophobicity, and the water won't stay on this surface. When it goes down, it'll rebound into the air and like rebound several times until it disappears. Next page. The first theory, we use Young's theory. It describes the tension between solid, liquid, and gas. So these are three tensions. Like this one is between liquid and gas, this one is between solid and liquid, and this one is solid and gas. Yeah. So by looking into these three forces, we can write down the equation like this. Yeah. Okay. So SG and SLLG cosine theta. When you drop a water on a high velocity surface, they produce a tiny structure that has bigger contact area. So the tension SL thus decreases, filling up the space between the drop and air. and minimize wettability. The next theory is Cassie-Baxter theory. The equation is a correction of ideal smooth surface because the theory we just talked about previously, the Young theory, is designed for a ideal and smooth surface. And this theory have a correction that to fit tiny structure situations. So by looking into this equation, we all have the sigma 1 and sigma 2. The sigma 1 is the total divided by solid liquid. You can see from this chart. So the orange part is total and solid liquid part is yellow. And the gas solid part is green and the total is still red. So by writing down this equation, we can conclude that sigma 2, the increase of sigma 2 makes cosine theta CB smaller than cosine theta, and theta CB is bigger than theta. So this creates a smaller contact angle. Moving on, we have the methods, the devices and design we use. These are the devices that we use. We placed a DC motor connected to a 9V battery. This is the motor, and this is the surface we use. And we release the drop on different radius spots to control surface velocity. Like these lines, we started from the middle, and like step by step go on to the bigger radius. And we record it with slow motion with the camera, and we use the software tracker to track the position of the drop. These are the control variables. We had three parts. First one, a surface velocity. We change the RPM and radius to create different surface velocity. B is initial height. We drop the water from the different height initially. This is the initial height. So the water goes down from here all the way to the surface. We change the height and C shape compression. We we look into the shape changing in the period of contacting the surface and go back to the air.
How is that a control variable? How do you control that?
Wow, good question. Like, I mean,
应该
the
说不是，它不是 control，应该说它是一个 variable，是提供什么？
应该是 ingredient 的咯。
所以应该有一些
Like, some of these are the result that we are trying to find out. And these three, the expression of the height, the operator h means the initial height, and h1 means the first rebound height, and hc means the center of the drop. The fourth part results are the experimental results and data analysis. First one is surface velocity. We set an initial height at 2 cm high and surface type is PC. We record and track vertical position changes and compare rebound heights, H1 and H2, and wetting time. So these are the radius from 1 cm to 5 cm, and the first rebound and second rebound. So you can see that in 1 and 2, these two cases, there's no rebound found. And 3 and 4 have one rebound. If you drop the water at 5 cm radius, it can rebound 2 times. And to the right, this is the time to wet. It means the time from the drop contact the surface first time to the time that it disappears. This figure suggests the surface velocities relationship with mass with the radius, and we track the mass center position of the drop. So from 1 cm to 5 cm, you can see that the 5 cm had 2 rebound spots, and 1 cm only had 1, and 3 and 4 had one rebound track. The second one is initial height. We set the radius at 5 cm and release the drop from different initial heights, and record and track vertical position changes. Compare rebound heights, the lowest center position, and contact angle. So we test the 3 different data from 2 to 4 cm heights and investigate the first rebound heights. We can see the bigger the initial height is, the bigger the rebound height is, and the bigger the lowest point HC is. This three picture is the drop at the lowest point as they contact the surface. From the left to right is 2 cm to 4 cm, and we use software to measure the contact angle. From 2 cm to 4 cm, the contact angles are 114, 124, and 160. So basically, the higher you drop, the contact angle will get bigger. This is the chart of the mass center position with different initial heights from 2 cm to 4 cm. And these three are the lowest point height, and these three are the first rebound height. And this is the surface velocity to mass center position. From radius 3 to 5, we measured the different surface velocity from 21 meter per second to 39 meter per second. So in this case, we can see from 20 meter per second to 40 from 20 meter per second to 40 meter per second. The rebound height basically remain the same and doesn't change much. So these four are their data convert into plots respectively. The last one we want to look, we want to research is shape compression. So we know that the water shape can be different in the period of contacting and rebounding. So we just track the center of mass, which is the light blue track, the light blue trace, and the deep green trace is the height of is the size of the drop. So we can see the drop initial size is like this, and when it contact the surface, it gets smaller and get bigger again. The normal size are the highest point and get bigger. Eventually, it disappears. So the picture to the right is the size of the water changes along with time goes by. The water has stressed and compressed, which each four of this period. We divide it into 4 periods, which is blue, red, green, and yellow. These are the 4 steps of contacting the rebounding. In the first step, water just get free fall from the initial height. And then when the period 2, the bottom of the drop always stay on the ground, but the size of drop can get smaller and stretched. In the period 3, the top of water drop basically remain the same, but the water size gets smaller and bigger again. In the last part, which is the fourth part, the water get back to normal size and slowly get disappeared. This is the compression rate of the drop in different radius, from 3 cm radius to 5 cm radius. We measure the size of the water when they are smallest. So the size gets small and get big again. We record this point, and the data is right here. From the radius 3 cm to 5 cm, the velocity is 21 meter per second to 40 meters per second. We can see the most small size is like the length of this blue arrow is from 0.00064 to 0.000450. So actually, we can see that as the radius get bigger, the most small size gets smaller. And are here we have our conclusion. The first one, surface velocity and rebound height. In the experiment A and C, we can see that there are 3 points. In the rather low velocity cases, the surface velocity determines rebound height. When it reaches a certain velocity, rebound height barely get anywhere higher. We utilize the setting we utilize this time are able to reach the highest of 0.0040 cm. This is the conclusion of initial height and rebound height. We can see in the experiment B, the drop rebounds higher as initial height edge gets higher. The higher initial height provides bigger contact angle, which means more hydrophobic. The conclusion of surface velocity and shape compression. We can see from the experiment C, shape compression. These are the two main points. First one, the water drop was compressed and strengthened twice and turned back to a round bowl shape. The higher surface velocity makes the drop compressed more with a bigger contact angle. These are the references that we refer to. And it's the end of my presentation. Thank you.